All right, let's talk about a really sneaky but super dangerous software bug. It's the kind of thing that has hit some of the biggest apps you use, like every single day. This is the story of that bug, and the really clever tools someone built to finally squash it.
So, let me ask you a question. What do Google Chrome and Firefox have in common? I mean, besides being our go-to for, watching cat videos.
Well, here's the thing. They've both been hacked using the exact same kind of subtle bug. It's a vulnerability that just loves to hide in plain sight, right there in the C++ code that makes these huge programs run.
So this bug, it basically creates this dangerous illusion deep inside the code. And yeah, it sounds like a magic trick, but believe me, the consequences are very, very real. The technical term for this is type confusion. And really, the whole idea is to trick a piece of software into thinking a piece of data is something it's not. The analogy here is perfect. Imagine you've got this big warehouse, right? An attacker sneaks in and slaps an apples label on a box that's actually full of oranges. Later, your program comes along, sees the apples label, and grabs its apple slicer. What happens when it tries to slice an orange? It's chaos, a huge mess. And that is exactly what's happening, just inside your computer's memory.
So how does this even happen? Well, it's because of something in programming called typecasting. And they're basically two flavors. First, you've got the safe kind, called an upcast. Think of it like taking a box of Granny Smith apples and just labeling it fruit. Totally fine, right? It's still true. But then, you have the risky kind, the downcast. This is like finding a box that's only labeled fruit and just guessing that it's full of apples. It might be, but it could also be oranges. And if you don't check first, well, your apple slicer's in for a really bad time. And that assumption, that's where all the danger is. And look, this is not just some theory. This line of code you're seeing, it's from a real hack that was used against Google Chrome. See how it's forcing the program to treat some generic node thing as a very specific HTML image element? The problem is, what if that node was actually, say, an SVG graphic instead? The program might try to grab memory that doesn't belong to it, or even worse, an attacker could trick it into running their own malicious code. It's the perfect backdoor.
Okay, so you might be wondering, if we know about this problem, why isn't it fixed already? Well, it's not for lack of trying. People have tried to build defenses, but they just didn't work. And that's our next chapter, the problem with the old way of doing things. The thing is, all the previous attempts to build a safety net for this stuff, they just weren't practical for the real world. For one, they were so slow. They added so much performance drag, you could never ship them in something like a web browser that needs to be fast. On top of that, they were incomplete. They couldn't even protect all the different kinds of C++ code out there. And maybe worst of all, they were just full of holes. They completely missed entire sections of memory where these bugs could hide, like on the stack.
And this chart, wow, it really tells the story. You look at the early tools, like UBSAN, and you see all these no's, major gaps. Then Calvert comes along, the next generation. It's better, sure, but it still only partially tracks memory and had some issues. And then you get to TypeSan. Just look at that column. Yes, 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 yes. It supports everything, tracks everything, it's thread safe, and you don't have to manually tell it what to ignore. It's just a clean sweep, no contest. And that, of course, brings us to the hero of our story today, TypeSan. This is the new guardian against type confusion.
What makes TypeSan so special is that its core idea is actually brilliantly simple. It just creates one single super fast map. And in that map, for every single object a program creates, it doesn't matter where, on the stack, the heap, anywhere, TypeSan writes down its one true identity. That's it. No more guessing.
So how is it so fast? Well, it uses this really clever system that basically mimics the page tables that your computer's CPU uses to manage memory. And because of this design, it can look up an object's true type based on its memory address in what tech folks call constant time. All that really means is that it's always fast. It doesn't matter how big the program is or how much data there is, the lookup takes the same tiny amount of time. It's incredibly efficient. It all boils down to a really simple three-step process. First up, instrument. When you compile your software, TypeSan automatically injects these little monitoring hooks into the code. Next, track. While the program is running, it keeps a record of every single object's true identity in that super fast map we talked about. And finally, check. This is the crucial part. Just before one of those risky downcasts is about to happen, TypeSan does a quick check. Does the label match the box? If not, it just stops the operation right there before any harm can be done.
Okay, so on paper, this sounds amazing, right? But the real question is, how does it actually perform? What happens when you put it to the test?
To find out,
The researchers set up a head-to-head battle. They pitted TypeSan directly against the reigning champ, Kavar, and they didn't use some easy test. They used the Spec Benchmark Suite, which is this industry-standard set of really tough programs designed to push systems to their limits. It was time to see who was stronger and faster. And the results? I mean, they're just staggering. Get this, on one single program from that benchmark, TypeSan checked and verified over 254 million risky typecasts. Let that sink in. That's the kind of insane coverage we're talking about here.
Okay, so remember that 254 million number? How many did the old state-of-the-art tool Calaver check on the exact same program? 24,000. Not million, thousand. That's not even in the same ballpark. We're talking orders of magnitude more checks. It's like TypeSan suddenly turned on the lights and revealed a whole universe of potential bugs that were completely invisible before.
But hang on, you're probably thinking, all that extra checking must make it super slow, right? That's the logical trade-off. Well, nope. Take a look at this. This chart shows the performance cost, the slowdown. Kaver, the old tool, slowed the program down by almost 30%. That's huge. TypeSan, while doing millions and millions more checks, had a performance hit of just over 7%. It's not just safer, it's way, way faster too.
So yeah, the conclusion here is pretty clear. You get this massive, revolutionary jump in security coverage, and you get it 4 to 10 times less performance cost. It's a total game changer. There's really no other way to put it.
And this is so much more than just some cool research project. This has huge, real-world implications for the software you and I use every single day. So let's wrap this up with the big takeaways.
So what's the bottom line? First, TypeSan is actually practical. That low performance cost means it can be used in real-world software, like web browsers. Second, it's comprehensive. It covers everything, all memory types, all class types, no more blind spots. Third, it's flat-out effective. It finds these dangerous bugs and stops them cold before they can be exploited. And maybe the best part? It's open source. That means any developer, anywhere, can start using it right now to build safer software for all of us.
And all of this leaves us with one last, pretty exciting question to think about. Now that we have this kind of powerful, efficient, always-on protection, are we finally, actually, getting a step closer to that old dream of making software that's truly unhackable?